Today what I want to talk about is work energy. This is chapter 14 in Hibbeler, and this is an overview. So I'll go over some of the derivations, not as in the type of detail that maybe I might otherwise, but just give you an overview of what's happening. Mainly out of this chapter, you've gotten one big idea, which is the principle of work energy. So you've dealt with particularly particles, and also now we'll talk a little bit about systems of particles, conservative forces, and finally just define what power and efficiency are. But the main thing to realize is that often work is a very particular kind of definition. You have to be moving in the direction of the force you're interested in. So here we have an example where one person is climbing a set of stairs and they're doing work. Another person is walking on a horizontal surface and they are not doing work. So work is a very well-defined sort of thing. And you have to realize what you're dealing with, even though, say, one person might displace 30 or 40 kilometers and still do no work as long as they're moving horizontally. Work is defined as displacement along the direction of force. So here, for example, work is done. They travel along this green path, and as they go out to the end, there's work done by that action because weight is displaced by this distance. However, weight is not displaced along this path, and so there's no work done in this case. And in all cases, work is a dot product, force dotted with dr. So that's kind of exciting because you'll notice that here I have two vector terms and no vector over here. It becomes a scalar, a magnitude term. If I consider a particle traveling also along a horizontal path, and it's at an angle theta with respect to that path, work done is going to equal in scalar form f ds cos theta. So a scalar form just means that I'm drawing it out and I'm just putting the magnitudes directly. I'm not calculating a dot product and I'm not looking at anything. So that will be typically, and the reason why we like normal tangential components, it's going to be the force tangential that does work. Force normal does no work at all and never does. Component of force acting along the path is one way of defining it, so F cos theta ds. The other one is to say the component of path acting along the force. I don't like that as much, it's just not as intuitive for me. But either way is correct. So you could say F times ds cos theta or F cos theta times ds. Units are joules and newtons per meter, or newton meters. If I look at something that's traveling along a path from point A or point 1 to point 2, the work done is just going to be the work from point 1 to point 2. And that's going to be F cos theta ds integrated from 1 to 2, or work 1 to 2. And if I define the path as S1 here and S2 here, then it's F cos theta S2 minus S1. Work is nice. It's not a vector. I don't need to know direction. I just need to know magnitude. We'll talk later about conservative forces, but it really kind of drives me nuts in this course that I have to not talk about them for part of the course. But at this point, you've covered the entire chapter, so I can discuss both or mention this now. If I do work in this, then that work is just going to be work fx dx, fy dy, and the work of the weight is going to go from, say, 1 to 2. Is going to work 1 to 2, 1 to 2, fx dx plus fy dy. And there, it's just going to be the component of force that's acting in the direction of motion, and that's going to be the vertical force. So work from gravitational forces moving from position 1, this really is kind of an arrow, to 2 is minus mgh. So as it goes up, it gets it's negative work. You have spring force, which is kind of a newish term. And so if I have a relaxed spring and I stretch it, then or compress it by the same distance, and delta x in both cases is exactly the same, I will have a force that's opposing the direction of motion. So as you stretch the spring, the force is going in the negative sense of the displacement, or pointing in the negative sense of the displacement. So the force of S is minus k delta x. And if I do the integration, I end up with this relationship right here, where I have corrected for the negative by just flipping the sign, or flipping the terms x1 squared minus x2 squared. So work 1 to 2, going from position 1 to position 2, or 2 here, is 1/2 k x1 squared minus k x2 squared, and that'll be negative in both cases. And it's the same value. That's kind of the interesting thing too. Doesn't matter whether you stretch or compress a spring, it always sort of behaves the same way. Forces that do no work, reactions at a frictionless surface, because force of friction is equal to 0. The more challenging one is the rolling without slip, and the reason why that is because it has 0 velocity. It does not displace, and because it does not displace, it cannot move, and so force of friction does no work. And then I keep telling you over and over that this course is entirely Newton's second law. And where is that going on? Well, we had sum of forces is equal to mass times acceleration. In chapter 12 in Hibbeler, or in the particle kinematics chapter, we define this relationship for acceleration. So we can use that relationship, and it's kind of neat because it has velocities and displacements and forces. So force, velocity, distance. If I integrate that, and I recognize that all of these forces are in the tangential direction of the path, I can write force tangential is equal, or ds, integrated from S1 to S2 of whatever path is equal to mass integrated from V1 to V2 of V dV. So I'm just splitting the derivative and putting the terms out. And so work from 1 to 2 is over here. That's just that expression right there. And on the other side, I have this new expression, 1/2 m v2 squared minus v1 squared. And I'm going to call T my kinetic energy. And I've been asked this in the past, why T? T is travail, and it comes out of French. So that's the reason why you have 1/2 m v squared, or T as your term. Power and efficiency. Power is the rate of doing work. So work per unit time. So force dotted with dr dt. And dr dt, you know, is V, is velocity. Units of watts and horsepower and all sorts of fun things in British units. And efficiency, which is the reason why we're all engineers, and which is really what you get for what you put in. Output work over input work, power out over power in. System of particles, what do you do? Same thing as you did before in kinetics, you sum them up. You have internal forces here, which will do work, but they'll be opposed by other internal forces doing the same work in the opposite sense. And then you have external forces that are going to do work on the system. Everything is with respect to the center of mass, G. So I have 3 particles, A, B, and C. I have to solve for each of those particles, so SI from position 1, SI2. So each I represents an individual particle. Sum up all the internal forces, sum up the work of external forces, sum up all the initial kinetic energies, and that's the final kinetic energies. So here you have T plus work plus, that should be T2, is equal to the final kinetic energy of the system. So I can sum it up for each of the individual particles. And only the external forces do work. The other thing is, I hate work as a way of dealing with conservative forces. On the other hand, we can often use gravitational, or for gravitational spring forces, they're conservative. That means that if I go from position 1 to position 2 and go from position 2 back to position 1, my energy remains the same. So it'll be, let's see, work 1 to 2 plus work 2 to 1 is equal to 0. That's a conservative force. Same thing with the spring. If I go from 1 to 2, 2 to 1, I will not gain and I will not lose any energy. I'll never gain energy, by the way, no matter what. Where I lose energy is usually with friction. So I end up with this expression. V2 plus V2 equals T1 plus V1 plus the work done from 1 to 2. And that is the important sort of relationship that I have for principle of work of energy. So work energy is force, velocity, distance. Newton's second law plays a role, and power and efficiency. Really, the payoff in this section is that the work at position 1 plus the kinetic energy and potential energy at position 1 plus the work done from 1 to 2 is equal to the final kinetic plus potential energy at position 2. And that's the conservation of energy. The important thing here is that this allows me to write this as all of the not so useful terms like friction. So if I want to do a conservation of energy problem, I'll have, say, gravitational potential, I might have spring potential, but the work done from 1 to 2 is going to be friction terms, and I can just eliminate or keep that as a separate term of only the work. And I find that for me, it's much easier to solve these problems. Thank you very much, and we'll talk again next time.